Hello. Today the topic about the detection of carbon dioxide and hydrogen peroxide on the stratified surface of Charon with JWST. Observations of Charon by the James Webb Space Telescope offer an unprecedented view at wavelengths never observed before and provide new insights into its formation and subsequent evolution. Charon, the largest moon of Pluto. Charon, Pluto's largest moon, is a captivating entity in the distant reaches of the solar system. Beyond the orbit of Neptune lies a collection of small celestial bodies known as trans-Neptunian objects, TNOs, which orbit the Sun and hold critical insights into the solar system's early history. These objects act as cosmic time capsules, offering scientists a glimpse into the primordial environment from which the solar system originated. Their unique surface compositions, physical properties, and dynamic behaviors serve as keys to unlocking the secrets of this ancient era. However, a significant challenge lies in distinguishing between pristine surface compounds and those altered by space radiation and micrometeoroid impacts over time. The ability to differentiate between these states is crucial for reconstructing the nature of the primordial disk from which these objects, including Charon, formed approximately 4.5 billion years ago. Among the many TNOs, only a handful have been closely examined by spacecraft, one of which is Charon, Pluto's largest moon. In 2015, NASA's New Horizons mission provided humanity with its first detailed look at Pluto and its moons, shedding light on the complex and fascinating nature of these distant worlds. Charon's surface, as captured by the New Horizons spacecraft, is particularly intriguing, offering a wealth of information that continues to puzzle and excite researchers. The enigma of carbon dioxide on Charon. One of the most perplexing discoveries about Charon's surface is the mystery of carbon dioxide. Images and data from the New Horizons mission revealed that Charon is pockmarked with numerous craters, each surrounded by bright blankets of ejecta-rich and crystalline water ice and ammonia-bearing compounds. These craters offer a glimpse into the Moon's subsurface composition, as impact events often expose materials hidden beneath the surface. Despite this, a curious absence has baffled scientists. No carbon dioxide was detected on Charon's surface, despite evidence from studies of comets and other objects suggesting that carbon dioxide should be present in the outer regions of the protoplanetary disk from which Charon formed. This absence is surprising, especially since volatile ices, which could obscure the detection of carbon dioxide, were also missing. If carbon dioxide exists in Charon's interior and is brought to the surface through impact events, why doesn't it appear in any of the data collected by New Horizons? This posed a significant challenge to scientists studying the Moon, as understanding the composition of Charon's surface could provide crucial insights into its history and evolution. The key to solving this puzzle lay in observing Charon's surface beyond the 2.5 micron wavelength limit of New Horizons spectroscopic measurements, where several ices, including carbon dioxide, have much stronger absorption bands. JWST unveils carbon dioxide on Charon's surface. The quest to extend the wavelength coverage of Charon's surface spectroscopy beyond 2.5 microns has been a long and challenging endeavor. In fact, it was one of the central goals of my PhD research, which began back in 2006. However, this goal proved difficult to achieve due to Charon's faintness and the limitations of the available observational technology, even with advanced instruments like the Very Large Telescope in Chile. The absorption of light by Earth's atmosphere further compounded these difficulties. While some insights were gained from these observations, it would take nearly 2 decades. The cutting-edge capabilities of the James Webb Space Telescope, JWST, and a highly skilled team to finally realize this goal. In 2022 and 2023, our team used the near-infrared spectrograph on JWST to conduct 4 separate observations of Charon, covering its northern hemisphere. These observations revealed carbon dioxide absorption bands at approximately 2.7 and 4.3 microns in all the spectra. While the presence of carbon dioxide was expected, the clarity and strength of these absorption bands exceeded our expectations. The quality of the JWST data allowed us to explore the nature of the carbon dioxide in greater depth. Key questions that arose included whether the carbon dioxide exists in its pure form or is mixed with other surface compounds, and why it isn't detected below the 2.5 micron threshold. A comprehensive analysis of these questions required us to integrate the high-quality JWST data with advanced spectral modeling and cutting-edge laboratory experiments. These efforts led us to the conclusion that Charon's surface is layered, with a top layer of pure crystalline carbon dioxide overlaying a subsurface rich in crystalline water ice and tholin-like materials, complex organic molecules. The upper carbon dioxide layer is likely brought to the surface through impacts, and the unique spectral properties of this layered structure explain why carbon dioxide is only visible at longer wavelengths. We also explored the possibility that some of the carbon dioxide could be formed in situ through radiation processing, adding further complexity to our understanding of Charon's surface. Hydrogen peroxide, evidence of radiation processing. In addition to the discovery of carbon dioxide, the JWST observations revealed another surprising finding: a spectral plateau around 3.5 microns. After careful analysis and comparison with laboratory data and similar JWST observations of Jupiter's moon Europa, we determined that this feature is indicative of the presence of hydrogen peroxide on Charon's surface. But what does the presence of hydrogen peroxide signify, and why is it found on both Charon and Europa? Its detection on Charon suggests that the moon's water ice-rich surface is actively altered by space radiation, including solar ultraviolet light, solar wind, and cosmic rays. This alteration process likely contributes to the formation of hydrogen peroxide on Charon. To test this hypothesis, our team conducted new laboratory experiments, confirming that hydrogen peroxide can indeed be generated on an icy surface exposed to radiation, even in the presence of carbon dioxide. Charon's complex and evolving surface. The discoveries made with JWST have significantly expanded our understanding of Charon's surface composition. Prior to these observations, the Moon's surface was known to consist of water ice, ammonia-bearing species, and dark tholin-like materials. However, the detection of carbon dioxide and hydrogen peroxide adds new complexity to this inventory, revealing that Charon's surface is shaped by both primordial materials from its formation and ongoing processes like space radiation. The surface of Charon, much like a cosmic palimpsest, retains traces of both its ancient past and the dynamic processes that continue to alter it today. These findings underscore the importance of continued exploration and observation of distant worlds like Charon. As we push the boundaries of technology and scientific inquiry, we uncover new layers of complexity in the objects that populate our solar system, offering deeper insights into their origins, evolution, and the forces that continue to shape them. Thank you.